specifically for the function AND or XOR. So the concept is very clear that we have this equation. We have this equation from the simple neural net. This one. So this can be written. We can write a straight line, which will be, if this is the form of x1 w1 and x2 w2, you can formulate a straight line from this equation, and from there, if the threshold is theta, then we can graphically represent them, and then let us apply this concept in linear separability, especially for AND function, OR function, and XOR function. Okay, so what is linear separability? Linear separability is that for each of these nets, the intent is to train the net so that it will respond with the desired classification when pretended with an input pattern that it was trained on, or when presented with one that is sufficiently similar to one of the training patterns. Before discussing the particular nets, it is useful to discuss some issues common to all the nets. Okay, for a particular output net, the desired response is a yes if the input pattern is a member of the class, and no if it is not. A yes response is separated by an output signal of 1, and no response separated by an output signal of -0. Normally this is -1 and -1 and +1 responsible for no and yes. Okay, sometimes it is also referred as 1 and 0, but here we are considering -1 and +1 and -1. +1 is for yes and -1 is for no. Okay, -1 is for no. Since we want one of the two responses, the activation function is taken into step function, because we want two types of responses, yes or no. So activation function has been taken as step function. The value of function is 1 if the net input is positive, and -1 if net input is negative. Sometimes if net input is negative, we can also represent it in terms of 0, but here we are representing in terms of -1. Now the net input looks like this. Just now I have written, this is the threshold bias, and this is the xi wi. It is easy to see that boundary between the region, this one, where y in greater than 0, and the region y in less than 1, which we call decision boundary. So if y in is greater than 0 and y in less than 0, if y is greater than 0 is a positive thing, if y underscore in less than 0 is a negative thing. Okay, so this is called decision boundary and is determined by the relation of this. Depending on the number of input units in the network, the equation represents a line, a plane, and a hyperplane. Okay, if there are weights, so that all the training input vectors for which the corrected response is +1 lie on the one side of the decision boundary. Let's say +1 is this side, -1 is this side. Let's say pluses and minuses. Then what it says on the other side, decision boundary, and all of the training input vectors for which the corrected response is -1 lie on the other side of the decision boundary. We say that the problem is linearly separable. That means, let's say I have pluses, I have minuses. If my decision boundary is able to segregate them, separate them, then we'll call it the function is linearly separable. That means a linear straight line in fact can separate them. Okay, linearly separable. But the problem is that for some functions this linear separability won't happen. And what is that function? We are going to see. For AND and OR it will be little bit easier. For function AND and OR, to separate them will be little bit easier. But there is a function. So I was discussing on linear separability. So linear separability means the function that I am taking, that function is linearly separable. Okay, so there is addition if you take, or function and function. Let's say these two functions are linearly separable or not. Okay, so this is quite an issue, because not all the functions are linearly separable. Given the plus and minus, let's say plus is coming in this side, minus is coming in this side. So in this case it is linearly separable. Okay, or maybe let's say something like this. Let's say pluses are in this side, plus minus. Is it linearly separable? I don't know, we'll see that. But what, okay, in this case, let's say pluses on this side and then minuses on this side, then also it is possible, let's say linearly separable, no issue. Okay, so we'll see that. And AND function, what will happen in the AND function also, that also you are going to see. So the problem itself is linearly separable problem. So remember that linearly separable problem is a quite a popular problem in case of simple simple neural net, because neural network sometimes for a particular function it is not able to, not sometimes, every time, there is a function for which neural network is not able to separate them linearly. Okay, so this is in 1988, this paper has been published by Minsky and Peppard, showed that a single linear net can learn only linearly separable problems. Furthermore, it is easy, I mean, if I give a function which is not linearly separable, that can be possible. Okay, some function like AND, if AND is your function, OR is your function, these two might be done, but there are functions which, there may be one function which is not linearly separable by simple neural net. Furthermore, it is easy to extend the result to show that multilinear nets with linearly activation function are no more powerful than linear nets. Okay, these also, from there we can also draw the conclusion that multilinear means we have not one layer but we have many layers as a hidden layer. Okay, multilinear neural nets no more powerful than single layer. That means theoretically what we can solve by a single layer neural net can also be the multilinear, whatever we can solve by multilinear neural net can also be solved by single layer neural net. Okay, this is there. It is convenient if the input vectors are order paired to the graph input training vectors and they indicate the desired response by the appropriate symbol plus or minus. The analysis also extends easily to nets with more input units. However, the graphical display is not as convenient. The region where y is a positive is separated from the region where it is negative by the line. So here you see it's an AND function. So you know the AND function, how it works. So AND function, this is the truth table for the AND function, right? In case of AND function, if both the inputs of AND gate, I am talking about AND gate, if both the inputs are 1 and 1, then it is positive, remaining all the cases is 0. Consider that if in case of 1 and you know 1 1 equal to 1 1 0 0 0 1 0 0 0 0. So this is, instead of writing 0 here, we are writing minus 1. Okay, just a representative. This is a representational. So 1 1 plus 1 1 minus 1. Minus 1 is nothing but 0 only. You just remember that. This is also minus 1. That means 0. And remaining all others, these all blocks are minus 1. Okay. So this is only one case. It is 1. That means when both the inputs of the AND gate, are 1 1, then only you will get one input, right? Now let us see whether it is linearly separable. So the two regions are called decision region. Already we have declared. Further, notice that the following example, there are many different lines that will serve the separate the input point that have different large target value. However, for any particular line, there are also many choices W1 and W2 and B that gives exactly the same line. The choice of the sign of B determines which side of the separating line correspond to +1 response and which side to a -1 response. There are 4 different bipolar patterns we can use to train a net with 2 input unit. However, there are 2 possible responses for each input pattern, so there are 2 to the power 4 different functions that we might be able to train a very simple net to perform. Okay, now let's say this is the situation we have. So in case of 1 1 1 plus 1 and plus 1, both the input x and y, if it is 1 1, then we have plus 1 here. Remaining all other case, it is minus. Okay, if it is if x is -1, y is +1, then also it is -1, and if it is -1 this is -1 okay, and this is +1 -1. Okay, so this is the graph, and then you see here this is the graph, and then for AND function, this is how the linearly separable things happen. But how it happens, like the desired response can be illustrated in figure 2.3. One possible decision boundary for the function is shown in figure 2.4. An example over there can be give the decision boundary illustrated, namely the separating line. So here x1 plus x2 equal to 1. Okay, x1 plus x2 equal to 1. This is the function. So if you free x2, it is nothing but minus x1 plus 1. So minus x1 plus 1 means x2 equal to minus x1 plus 1, right? So this is how you do. So in this case, what is happening? Yeah, so here in this case, if you compare it with W1, and because R's is nothing but what is the function you have? We have this function, right? X2 equal to this, x2 equal to this, right? So x2 equal to, so here you see W1 by W2 by x1. Okay, W1 by W2 equal to x1, and this one B by W2. Okay, so here B1 comparing this, let's say this is equation X, let's say this equation X, if you compare it with this one, equation 1, let's say, then it will be minus B equal to minus 1, true, B equal to minus 1. Okay, this is minus 1, true, if you compare it, and W1 and W2 is plus 1. Okay, so the choice of sign of B is determined by the requirement that B plus W1 plus x1 W1 plus x2 W2 less than 0. Okay, so anyway, this equation can be written like this. So in this case, this AND function is actually has been separated. These all three minuses are in one side of the boundary. Okay, and this plus is in another side of the boundary. Okay, so this is linearly separable. And you can create the function here, no problem. Okay, this is for AND function. For OR function, we have this truth table is this. In OR function, we have many combinations of 1. When the input or how it looks like, this is the OR gate, right? So in case of OR gate, we have 1 when both are 1 1 0 0 1, everything is 1 except that if both are 0 0, then it is 0. So both are minus 1 it is minus 1. Remaining all three other conditions, we have 1. So in this case the weights must be chosen to prove separately line and illustrated in figure 2.5. One example suitable weight is this, B equal to 1, W1 equal to 1, and this. So here x2 equal to minus x1 minus 1. So the separating line is coming in this weight is coming. Okay, the choice of sign B is determined by the requirement that B plus W1 x1 plus x2 W2 greater than 0. So here all pluses are one side of the straight line, this one, these three, and the minus is in another side because only one minus is there. So this is linearly separable. This is also the OR function. The OR function is also linearly separable. Okay, fine. But the problem arises when, so the preceding two mappings illustrate graphically the concept of linearly separable input. The input point to be classified positive can be separated from the input points classified negatively by single straight line. The equation of the decision boundary are not unique. We will return to this example. Okay, so this is done for AND function and OR function is done, but the problem starts when it is a XOR function. So you know that XOR function is somewhat different, right? So XOR function when either of the input is 0, when the inputs are complement, right? If one input is 1, another input is minus 1, then only plus the positive responses come. Remaining when it is 1 1 minus 1, that means when it is 1 and 0, then you will get 1, or if it is 0 and it is 1. So you are not writing 0, we are writing minus 1. So in both the cases it is 1, right? These two are the 1, and remaining this and this minus 1. So you see, in case of 1 1 it is minus 1, in case of 1 minus 1 it is plus 1. Sorry, in case of 1 minus 1 it is plus 1. Here 1 minus 1 it is plus 1, and then minus 1 1 minus 1 1 also plus 1, right? Minus 1 plus, so x is minus 1 and y is 1. So what I'm trying to say, these are the two cases, positive cases. When x is 1, that means this one, and y is minus 1, this is positive. And when x is minus 1, this one, and y is 1, then also it is positive. So these two are the positive instances. But how do you separate it? You cannot separate with linear function. That means with the straight line, you cannot have a straight line. If you have a straight line here, it won't be separated. If you have a straight line here, it won't be separated. If you have a straight line here, it won't be separated, because it is something like this: plus plus minus minus. In case of XOR I am talking about, you cannot have a straight line which will separate it. You cannot have a straight line here. If you put straight line over here, then plus will come and one plus will remain here, right? This is the problem with the linear separable. So XOR function cannot be solved with the simple linear separability concept. It is not linearly separable using simple neural network. That is the intention. Okay. So further discussion also can be done, but this is the catch here. That XOR function cannot be solved, but OR function and AND function, these two functions can be separated. The inputs can be separated for these two. The output of these two functions can be separated by simple straight line, and that's why these two functions, the output of these two functions may be linearly separable. But in case of XOR, the output, it is not. The XOR function's output cannot be linearly separable by simple neural net. Okay.